PCB Foundations, by Paul Taubman and Sean Kelly. Presented by 9.Connects. Chapter 6. Project Design Flow. 6.1. Introduction. Although no two projects are alike, and some have very specialized aspects, most design flows can be described in the following diagram. These steps will be further explained throughout this chapter. 6.2. Project Needs. Before a design can begin, the project needs should be understood and agreed upon. These needs may come from a client, a marketing group, upper management, or several engineering disciplines. At a high level, this might include things like, but not limited to, general performance and features, industrial design, size and look, environmental requirements, reliability, regulatory requirements, cost, schedule, life cycle. 6.3. Specifications. A good design starts with a specification. From the requirements that are flowed down, detailed specification documents need to be written with the concepts presented in the previous chapter. These specifications should be well stated, concise, and not open to interpretation. In addition to what the general requirements are, the specification needs to include details that are very specific to the PCB development. For most designers, if given a choice between drawing schematics or writing a specification, schematic capture is the preferred activity. It is one of the more visible aspects of the project. For a management that wants to see progress, the drawing of a schematic is one of the best ways to show it. Unfortunately, a project that has no specification is often riddled with hundreds of conflicting emails, spontaneous redirections by management, and countless meetings. It also causes much consternation with vendors who are asked to perform deliveries that are short of being miracles, only to find out the next day that the effort has been scaled back or scrapped. Specifications also allow for a reality check. All too often, we are asked to design things which may not be all that easy to do. By creating a specification, questions arise that force everyone to reconcile them sooner than later. Has that been done before? Do we have the capabilities in-house to do it? How are we going to test it? Specifications can be just as much an exercise in feasibility, as it is an exercise in writing testable requirements. Think of the specifications as the marching orders for the design. 6.4. Starting your project. Once the specification has been written and agreed upon, the designing can begin. For designers, this usually starts with the schematic. For mechanical engineers, it should progress in a way so that they'll be able to hand over the mechanical requirements of the PCB by the time the layout is started. For test and manufacturing engineers, test and production fixtures need to be started, so that prototype testing can go through the debug process. One of the pitfalls of EDA tools is the reliance upon a push-button solution to generate the manufacturing documentation. We need to understand what documentation is needed, what is in the documentation, and more importantly, what is missing in the documentation. For example, bill of materials is often put together by hand because the libraries are not properly formatted. Schematics are difficult to read because net names are not applied, or details are not explicitly noted. Assembly and fabrication notes that give specific instructions are often missing. Knowledge of what documentation is needed is as important as the documentation itself. And, most importantly, it is the understanding of how your document package gets formed. Therefore, understanding the project flow is critical. 6.5. Schematics. Printed circuit design is accomplished in an EDA tool. Although there are a few other options to create designs, an EDA tool is the most preferred and efficient method by professional designers. Designs start with the creation of the schematic, and guided by the specification. Schematics are dimensionless representations of an electrical circuit, consisting of symbols which represent components. The ANSI/IEEE Standard 315A defines over 100 different symbols for the various components available. To interpret a design, one must recognize a symbol to understand the component it represents. Fortunately, many symbols are archaic, and will only be necessary if you are planning on reading schematics from decades ago that have components like vacuum tubes, or are planning to make use of these archaic components. The objective of the schematic is to tell a story of the circuitry that will eventually be fabricated on a printed circuit board. From the schematic capture, several important documents are derived. Schematic sheets, the circuitry in a graphical form. Good layout and labeling of a schematic allows for the review of the design by the design team. It also provides information that may be useful for those who will be testing, and possibly debugging, the design on the resulting physical board. Bill of materials. A good schematic, along with a good library, will enable the designer to create a bill of materials automatically. This may sound premature during the design process, however, there are considerations that need to be given to cost, lead time, and possible obsolescence. It is far better to find these issues prior to the next step of PCB layout, than to discover these issues when the board is being fabricated. Netlist. A netlist is generated by the EDA tool from the schematic. The netlist contains the reference designators of the components, and the connectivity of the pins in the circuit. This allows the PCB layout editor to provide connectivity guidance in the form of connection lines. In PCB lingo, this is referred to as a rat's nest. In most EDA tools, the netlist information can be passed along by invoking the necessary commands, or by importing or exporting this information between the schematic and PCB editors. 6.6. Library. The schematic library editor goes hand in hand with the schematic capture. It can be argued that the library's order in the process generally comes prior to the schematic. Without placing symbols from the library, the schematic design cannot be started. In a perfect world, the library editor would be irrelevant if all the components on the market were readily available in a common library format. However, with over 1 billion components in existence, and no common graphical format for the library between EDA tools, such a comprehensive library does not exist. As a result, a designer may spend just as much time in the library editor as they do in the schematic editor. There are advancements being made to assist in the creation of library components. Some are cloud-based, on-demand part creation services. Some are very extensive libraries, provided by large part distributors like DigiKey, or commission-free databases like Octopart. With all that, it is still the designer's responsibility to verify any component data from a third-party source. There is a fair chance that the part needed is not available through these channels, so be prepared to create your own. Most EDA tools will not allow the user to draw components in the schematic editor. This is for good reason. In addition to causing issues with the netlist, a component that is drawn with lines and arcs has no intelligent information associated with it. Although more detail will be presented in the chapter regarding libraries, it is enough to know that a good component has parametric information to assist with the creation of the bill of materials, and a link to its footprint representation for use in the PCB editor. Regardless of the library structure or component management system utilized, all libraries provide. Number 1. Symbol graphic. A symbolic representation of the component to be used in a schematic capture tool. Number 2. A link to a footprint representation of the component. Footprints are drawn in another library tool dedicated for that purpose. A link between the symbol and footprint representation is necessary, to allow for an easy transfer of information between the schematic and the PCB layout editors. Number 3. 3D body representation. Although not all EDA tools support this feature, it provides the ability to check for clearances for both the components on the board, and for fitment to mechanical structures surrounding the board. With the complexity of today's designs, 3D bodies are as important as the symbols and footprints. If the tool provides this capability, one should use it. Number 4. Intelligent data. This is a nice way of saying attributes, metadata, or parameters, depending on which tool one is using for their PCB design. This data provides information as to the characteristics of the components such as value, tolerance, temperature range, etc. It also provides information that allows for the rapid assembly of a bill of materials, such as manufacturer's name and part number, datasheet location, and description. 6.7. PCB layout. The PCB layout is where the circuits within the schematic start to take physical form. Component footprints are placed on the board, and the copper traces are routed, to allow these components to send electrical signals to each other. This effort is guided by design rules, with the understanding that the design rules are only as good as the designer who implemented them, and understands why they are there. Because the PCB layout is very mechanical in nature, MCAD, mechanical computer-aided design, tools can be used to assist with. Number 1. The creation of the board shape, especially if the board has some unusual dimensions and curves. Number 2. Creation of 3D component bodies to assist in component placement suitable for both the electrical and mechanical aspects of the design. Number 3. Collaboration between the PCB layout editor and the MCAD tool for interference checks between the board and enclosure for electrical and mechanical aspects. Documentation provided by the PCB layout includes, but not limited to the following. 6.7.1. Layer Stackup. The layer stackup provides an overview of how the PCB should be constructed, and provides the EDA tool with the layer availability for traces and planes. The stackup should be approved by the fabricator prior to the start of the PCB design. In turn, the fabricator can provide design rules that will keep the board within the fabricator's manufacturing tolerances. In high-speed designs, the fabricator can also provide trace width and spacing of traces, known as trace and space, for desired impedances on each layer. The stackup consists of copper thickness, based on the weight of copper in ounces, dielectric material, type of insulator and thickness, copper layer name and function, wherein the stackup the copper exists, and the use of it, mask material and thickness, defines what covers and protects the copper. 6.7.2. Pick and place files. This file provides information that will assist assembly in automating their equipment for stuffing the printed circuit board with components. 6.7.3. Drill files. The drill files provide the hole sizes and strike points for the drills. For the ODB++ and IPC 2581 standards, drill information is contained within the dataset. Those using the Gerber standard will need to provide drill information in a separate file, in addition to the Gerber files. 6.7.4. PCB layer printouts. Printouts of the design can provide details for those reviewing the PCB, in addition to providing information to those who may be testing and debugging the board after they are fabricated. With the use of laptops and the EDA tools, the need to print out hard copies is less common. 6.8. Chapter Summary. Documentation is required for all stages of fabrication and assembly of a PCB. This chapter briefly outlines the design flow to put the documentation needs into perspective. In the end, this documentation will be used to instruct a human, or equipment, in either the fabrication or assembly of the PCB. Remember that both humans and the equipment are following the instructions provided in these files. DFM and DFT are not instructions, but rather concepts incorporated into the design flow.